Okay. So today we'll review, and then we'll talk about if you have an operad in spaces, it gives you a monad in spaces, but then it also gives you a monad in base spaces. So that's called reduced monad. We'll talk about that. It's, I guess, big picture, what we're trying to do over the next, I think, like 4 lectures is to prove the recognition principle. So we'll talk about the recognition principle for free algebras over the little cubes operad, and then we'll talk about free resolutions in sort of the context of algebra, and then we'll talk about classical algebra, and then we'll talk about monadic bar resolution, which gives you free resolutions in the context of monads. Okay. So yeah, so recall that so we have this fixed category C, which maybe most of the time will be spaces, and then a monad is a functor from C to C, and a natural transformation that sort of serves as the unit, so a natural transformation from the identity to M, and then a natural transformation from M composed with M to M that satisfies unit and associativity axioms, giving this the structure of like a monoid object, if that's terminology you like. Okay. And an algebra over a monad is an object of the category, and a morphism in the category from the functor applied to the object that makes diagrams commute. And you should think of this as sort of analogous to like a group action, or if M is a group. Okay. And the most important, the primary example of monads that we'll be considering is the one coming from the little cubes operad. So the kth space of the little cubes operad is the space of embeddings of cubes into of k cubes into a cube, which are sort of standard embeddings. So they're just compositions of translations and coordinate axis scalings. Oh, is there can some people not see the PDF? Should I exit and reshare?
I can see it now. Thank you.
Okay, yeah, I don't know what I did, or what happened, but okay, great. Yeah, so so given the little cubes, there's this functor which sends a space to this other space, which this is the space of it sends a space x to the space Cnx, which is the set of cubes in a cube labeled by points in X. Okay, and because these spaces assemble to form an operad, this functor has the structure of a monad. That was sort of the main thing that happened in this course last week. Okay, and the main theorem that we want to prove is that if you have a connected algebra over the little cubes operad, then it's homotopy equivalent to an n-fold loop space. So this is called the recognition principle, and gives you a way of recognizing when a space is homotopy equivalent to an n-fold loop space. And historically, these kinds of theorems were useful or were for building models of spectra. But I'm not going to focus on that in this course. Yeah. So the proof of this theorem. Yeah. Oh yeah. So for the remainder of the course, what's the plan? We're going to prove this theorem. That's going to take 4 lectures or so. Then I'm going to sketch a proof of bot periodicity using ideas from classifying spaces. And then there'll be Thanksgiving, and then there'll be some talks after Thanksgiving. Okay. Yeah. So here's the proof strategy for proving the recognition principle. We're going to prove it for free algebras, and then we're going to resolve general algebras by free algebras. Yeah, and the proof for free algebras is going to involve ideas from scanning. Okay. So here is an analogy. Like, I guess this theorem is true, but it's not particularly useful, but it will inspire our proof of the recognition principle. So, okay, so it says, suppose P is a property of abelian groups, and let's say it holds for free abelian groups, and let's say if you have a chain complex and it holds for each term in the chain complex, then it holds for the homology of the chain complex. So this is the assumption, and then the statement is then P holds for all abelian groups. Okay, again, I said, like, I don't know of any actual interesting applications of this theorem, but the idea of this theorem will be analogous to how we prove the recognition principle, which yeah, is maybe non-obvious. Okay, so let's assume that P holds for free abelian groups, and let's assume that P, let's assume these 2 properties. How are you going to prove it for Z mod 7? Any guesses?
Well, you construct a chain complex that has Z mod 7 as homology.
Yeah, so you're just like, okay, let's take Z multiplication by 7, Z, everything else 0, and then H0 of C star is Z mod 7. So sort of philosophically, what you should sort of think of, like in this particular example, you should sort of think of this chain complex. You should sort of think of this chain complex as being equivalent to the chain complex Z mod 7. So, you could say, like, this is a chain complex, that's a chain complex. You can think of them as being equivalent. And so the idea sort of, it's not true that it's not true that every abelian group is free, but if you sort of put on your homotopy theory goggles and just view abelian groups as examples of chain complexes that are concentrated in a single degree, then, up to homotopy, everything is free. So if if you have some like homotopical property, you just need to prove it for free things. Yeah, so this is okay. So this is going to be our idea of how to prove the recognition principle. We'll prove it for free EN algebras, and then we'll show that in some homotopical or simplicial sense, everything is equivalent to something that's free, and then we'll deduce the theorem. Okay. Yeah, so let's review what free means in this operad or monad context. So if O is an operad, then the operad structure makes this functor, that sends a space to disjoint union of the kth space of the operad crossover symmetric group with the space of the k. This gets the structure of a monad, assuming O is an operad. And then, and then I guess maybe I should say that last time we said that like this is a free O algebra. And what did we mean by it's a free O algebra? Well, like if A is an O algebra and X is some object, then if this horizontal arrow is a map in the underlying category, then there's a unique red map like this, making the diagram commute, where the red map is a map of O algebras, and the blue maps are just maps in the underlying category. Yeah, so you should think of the monad associated to an operad as the free algebra functor, and it makes the usual diagram for free things. Like it satisfies the usual diagram for what you'd expect a free thing to be. Okay. So so the little cubes is an operad in spaces, and it gives you a monad in spaces. It's going to turn out that that basically for all the operads that I care about, you can also build a monad in base spaces. Okay, so let's just for simplicity, let's take an operad, and we'll assume that in arity 0, we just have one entry, and we'll name that entry 0. Then given a element in OK, we can build this O prime. So maybe in pictures, let's say little o in the little cubes example, say is 1, 2. O prime is going to be it's going to be that. Because so here, what is 0? 0 is no cubes in a cube. What is 1? 1 is a full-sized cube in a cube. So when you plug in 1 into the first k-1 slots and 0 into the last slot, you just delete the last cube. So this is what O looks. If this is what O looks like, this is what O prime looks like. And then this O tilde will be it'll be a quotient of the usual monad associated to O by the relation that if xk is the base point, then you throw out that cube. Yeah, so what you should think of in the case of the little, maybe that's the next slide. Yeah, so so what you do is, if an entry in your, this is a functor from, O tilde is a functor from base spaces to base spaces. And, it's the quotient of the usual free O algebra by this relation that if one of the points in x to the k is labeled by the base point, you compose the operad, you plug in 0 into the operad there. And this is going to have the structure of this reduced monad will have the structure of a monad in base spaces. So O is an operad in spaces, but it still gives us a monad in base spaces. Yeah, okay, so let's sort of see what this construction is in examples. So remember that com is the operad that has a single point in all degrees. And yeah, so what is com x? So this is the usual monad associated to com applied to x for x's space. And then we'll try to figure out what the reduced one is. So, I guess com x is going to be com k cross yeah, so do we have a so what's an alternate description of this? The thing underlined in blue. Yeah, it's just the symmetric product. I guess everything is the symmetric product. Yeah, so the blue part, maybe we'll just do this in steps. The blue part is going to be, so this is a, so because com k is just a point, this crossing over with a point just means quotient. So this is x to the k mod sk, which, this is what we called sim kx. And so the whole thing is sim x, which sometimes we called n of x. Any questions? I'm happy to repeat an explanation for any of these equal signs. Okay. Yeah, so it's the free abelian monoid on X. So what happens if you do this reduced construction? So now X has a base point, and he guesses at what the reduced monad on X is going to be. Yeah, so yeah, without looking at the, let's say, don't look at the formula. Just like what's some quotient of the free abelian monoid on X involving the base point? So, Yeah, I don't know. So like, what's a?
Can you literally like mod out by the base point?
Yeah, so that'll be the answer. So, yeah, so, yeah, so you can think of it as configurations of points in X that vanish if they go to the base point, labeled by the natural numbers. Maybe it takes. Yeah, so the free abelian monoid in X modulo the relation that X is 0, which is just n of X mod n of X naught. The way you sort of see it from this definition is this equivalence relation. So in the com case, all of the OKs are just a single point. So O is in com K, and O prime will be in com K minus 1. And there's a formula for what O prime is, but here you can just forget that formula because com K minus 1 is a single point. So telling you that O prime is in com K minus 1 tells you exactly what O prime is. It's the unique point. In general, we care what O prime is depending on O, but it's the space of the single point, so we know what it is. And so then, so here, basically you can forget the O parts in the com case because it's just a single point. So what is this saying? It's just saying we're imposing this equivalence relation that a point vanishes if it's labeled by the base point. Right? That's what this line says. Yeah, so that's how you would figure out what the reduced monad is from the formula. Any questions? Okay. So yeah, so in commutative case, it's free abelian monoid modulo the relation that the base point is the identity. Okay. So in the little cubes case, it's going to be maybe I should have written equivalence instead of equals. Yeah, so the reduced monad is just the quotient by the equivalence relation that cubes labeled by the base point vanish. So in particular, if X is connected, then this reduced monad is going to be connected because you can just take a path. If X is path connected, you can just, whenever I say connected, I basically always mean path connected. So if X is path connected, then this reduced monad will be path connected because all of the labels, you can just take a path from them to the base point, and then all the cubes will vanish, and you'll get to the point with no cubes. Okay, so yeah. So, this space is the space of cubes in X. This is the space of cubes in a cube labeled by points in X, and this is the space of cubes in a cube labeled by points in X with the equivalence relation that if a point is labeled by the base point, it vanishes. Okay. Yeah, so if we have an operad, then with this condition that the space of 0 to 1 operations is just 0, then the reduced monad, I guess, I forget, am I supposed to be capitalizing X? I don't know. is naturally an O algebra. And oh yeah, so what does this proposition say? Oh yeah, so first of all, this proposition sort of has two parts. Maybe I should have broken it up. So the part circled in light blue basically says that if you have a am I, is this right? Yeah. Yeah, so what's, someone can tell me if I'm wrong. So, okay, so if you have an operad, if A is an O algebra, then there's a map like this. Well, concretely, what is that? That means for each K, you get a map from OK times A to the K cross over the symmetric group. We can just forget cross over the symmetric group. Yeah, I guess we'll get a symmetric group invariant map if you'd rather, like that. And then now you can plug in, so we get this for each K, and then you can plug in 0. But, in this case, this is just the set containing 0, because A to the 0 is a single point, and our assumption, oops, typo. I don't know how to. Sorry. Trying to fix this typo. Why can't I write? Okay. That K is supposed to be 0. Yeah, so when you plug in K is 0, then the space on the left is just a point. So you get a map from point into A. So a map from a point into a space is the same data as, that's the same thing as a base space. So the upshot of what's highlighted in light blue is the statement that if you have, under the condition that O of 0 is a single point, then an O algebra in particular is a based space. There's a preferred base point, it's just the image of this one-point set mapping to A. Okay, so that's the first part of the proposition. The second part says that that the data of a map of base spaces from X to some O algebra is the same data as a map of O algebras from the reduced monad on X into A. Like X is not supposed to be in. Oh yeah, there's a LaTeX error. I need more parentheses in my commands or something. Okay. Yeah, so this last sentence says that OX satisfies the diagram associated with being a free thing. So this reduced the reduced monad evaluated on a space, we're going to call the free O algebra on X. And the second sentence says it satisfies the correct universal mapping property. I guess we're calling, I said I'm calling it the reduced free O algebra, or maybe a better thing would be to call it the free O algebra in the category of base spaces. Yeah, so it satisfies whatever diagram you would think. It satisfies the correct diagram for being a free algebra in base spaces. Okay. So now I'll sort of tell you about the scanning map, and it's going to be so it's going to be, I guess, a map of it's going to be a map of algebras over the little cubes operad, or a map of algebras over this monad. Okay, so but just as a map of spaces, it's going to be a map like this. So it's going to be a map from this, given some cubes labeled by points in X, we need a function from a cube into suspension on X. Yeah, so we'll think of this loop space as the space of maps from a cube rel its boundary to X, smash the cube rel its boundary, I guess basic maps. And remember, smash product is the quotient of Cartesian product, where you mod out by like base point in one space across anything. Yeah. Okay, so let's see, what's a point in this cube space? It's a collection of embeddings and a collection that points on X. And remember, they're not ordered. These embeddings are disjoint, that have disjoint images, and they're not ordered. None of these things are ordered, but they're like the symmetric group is acting diagonally, so you know which point is associated to which embedding, but you don't have it in global order. And then the formula is going to be, we're going to send this configuration of points and embeddings. Well, we need to send it to a function. So this thing is a function. We'll plug in m is a point in the cube, and if m is in the image of v, if m is in the image of fi, so if then m will be equal to fiv, and we just send it to the point xi smash v. So v is a point in a cube, so that's here, and xi is a point in X, so that's the output we want, and then otherwise you just send it to the base point. Okay, so I don't think it's possible to understand this just like in formulas, so let's sort of think in pictures. So so this is the formula. Any takers for where we want to map, qualitatively, where do we want to map the red point and where do we want to map the blue point? So I guess M. So the blue and the red point are playing the role of the M's. And then Greek letter is this configuration of cubes. So the scanning map applied to this configuration of cubes is a function that inputs points in a cube. So one of the red M or the blue M, and then the output should be in X smash cube rel its boundary. So basically, given a point in M and this cube, we need a point in X and a point in maybe I'll call the blue point N. Yeah, so we'll fix this. So S, squiggle. What Greek letter is this? I don't know. So this is the function. So let's say we evaluated it on N. So what is this? It's going to be something in X smash something in the interval. So any guesses for what point in X we want to associate to N?
Y? Y should be an X, right?
Yeah. So, okay. Y, and then now we need a point in the cube. And it's maybe a little harder to say, but, you know, qualitatively, what point in the cube do we want to associate to N? We want this point. So what you do is you know, this square, we have a chosen homeomorphism from this square to the full size square.
Yeah, it's like the point that maps to that blue point, right?
Yeah. Yeah. So let's say we, where would we be, like here or something? You know, I'll call this, I don't know, I'll call this I or something. Yeah. And so let's say that I, you know, whatever our embedding takes I to that point, then I'm bad at annotating. Yeah. Then we want that I. And then similarly, what do we do? S of Greek letter applied to M. You know, what point in X do we want to associate it to?
Base point?
Yeah, base point. And then what, you know, base point smash anything is going to be the same thing. So it doesn't matter what you write.
Right.
Right, like boundary of the cube. So, you know. And then you can check that this is that this is continuous. Like as if this point were to somehow, like, you know, walk to the this point were to exit the cube, this point would exit the cube, and then the I coordinate would go to the base point, and yeah. Similarly, you know, a cube vanishes if it's labeled by the base point, but that's fine. You know, that's compatible with the map. So the upshot is this map is continuous. So we get, yeah, we get a map of spaces. Any questions before I delete the pictures? Yeah, so we get a map of spaces. You know, for each space X, you get a map from the reduced monad on X to loops and suspension n X, and this is going to be a map of algebras over the operad, etc. Okay, so, you know, there's a theorem, and you prove it the usual way with quasi-fibrations, etc. That if X is connected, then this map is a homotopy equivalence. Okay, so yeah, and you need somehow this connectedness for there to be inverses up to homotopy, and whatever. Checking step 4. You know, checking step 4 of the quasi-fibration criteria will use that X is connected, because you'll need that somehow that stabilization maps are homotopy equivalences, and if you like stabilize by bringing in a cube labeled by a point in X, that's homotopic to the identity, because you can just sort of walk the label of the cube to the base point, and then the cube vanishes, and then you didn't stabilize by anything. That's how X being connected is used in the proof. Yeah, but so just, you know, maybe quick check, like, so this, I claim that, you know, being connected is completely necessary. I mean, you can check that if X is not connected, then the map is not an equivalence. And in fact, map is not an equivalence. Probably the spaces aren't homotopy equivalent, although it's harder to rule out some exotic homotopy equivalence. But definitely this natural scanning map is not an equivalence. So what's in terms of familiar spaces, what is this space? So maybe here's like a hint. So like tilde CNX is going to be CNX parentheses minus base point if X is discrete. So
does this have configuration space?
Yeah.
This one on a cube?
Yeah. So yeah, I mean this pictures added.
Because it's like little cubes labeled by a single thing.
Yeah. So if S naught is going to be, I don't know, base point and other point, I don't know what the other point should be called, X1, then anything labeled by X naught vanishes. So all we need is just things labeled by X1. And so it's just the space of cubes, and then that'll have the homotopy type of just the unordered configuration space. So let's see, what did I write? So this space is just homotopy equivalent to the unordered configuration space. The suspending spheres just increases the number. So this is just loops n suspension n. You can check that they have different fundamental groups. So like if n is at least 3, then let's write pi 1 of conf k Rn is going to be sk if, let's say, if n is greater than 2. On the other hand, pi 1 of this is z mod 2 if n is bigger than 2. And the symmetric group is not z mod 2 usually. N factorial is often not, or k factorial is often not 2. Sometimes it's 2. So these spaces are definitely different. It's true that somehow, like as you send k to infinity, this becomes a better and better approximation of that space. And we'll talk about that a little bit more, but so definitely just like this assumption is necessary. So what the idea is that these loop spaces, all the connected components look the same, and somehow when X is not connected, the connected components of this space get more and more complicated. Like in this configuration space case, depending on like when you have more and more points, and so this approximates that space when X is not connected, but when it's connected, they're actually homotopy equivalent. Okay, so and if you want to read a correct proof that a scanning map is a homotopy equivalence, this paper by maybe it's a book by Peter May, Geometry Iterated Loop Spaces, is the proof that I'm most sure is written correctly. It is not necessarily the easiest to read. Like, when you say false things, it makes the argument seem easier. Yeah. So, but at least I haven't checked all the details, but it looks like he's being super careful, which sometimes is annoying because then you're like, lots of details. Okay, so so basically, this result says if you have a free algebra, then it's connected. X being connected is equivalent to this cube space being connected. So if you have a connected algebra, then it's homotopy equivalent to a loop space of something. So the idea is we're going to try to use this to prove the result for the results in the free case, to prove the results in general, using ideas inspired by the cartoon theorem, theorem that if a property holds for free abelian groups, and it holds, and then like if it's preserved by taking homology, then it holds for all abelian groups. So that's the idea. So now we're the next remainder of today and the next few lectures will be about that idea. Okay, so let's just sort of talk about resolutions in the world of algebra for a while, and then we'll return, classical algebra, then we'll return to the world of monads. So, R will be a ring and M will be an R module, and a free resolution is of M is just an exact sequence like this, where all of the WI's are free. And so you can, in this case, W will be M will be W0 modulo the image of W1. That's what exactness says. So for example, this chain complex that I talked about earlier is a free resolution of Z mod 7. Excuse me. Yeah. And you can sort of rephrase what a free resolution is homologically as saying it's a chain complex where the zeroth homology is the group that you're interested in, and and all the higher homology vanishes. And are there people who took Manuel's infinity categories class last semester? Okay, a few people. Yeah, so you want to say he presumably talked about model categories, and you can say that this is like a W star is like a cofibrant replacement of M in some model category. Okay. And not only does this W star has the same homology as M. Oh yeah, but W star means take the chain complex but throw out M. So put W in degree 0 and throw out M, and then just take all the W's. Yeah, so you can, if you think of M as a chain complex concentrated in degree 0 and W star as a chain complex, then you get a map of chain complexes, and this is an isomorphism on homology. So you can think of W star as somehow it's a replacement of M, and it has the advantage of M in that everything is free, but the price you pay is that W is a chain complex. So not only is it not concentrated in a single degree, but there are maps that are important. So everything is free if you're everything is free up to homotopy if you're willing to pay the price of replacing your modules with chain complexes and modules. Okay, so one thing to say, if you have a free resolution, well, then what does free mean? It means it's free on a set. So, if we, I guess we're naming the maps, naming the map. So this F0 is going to be, it's surjective. That's what exactness means. And so if you look at F0 of S0, that's going to be a set of generators for M. Yeah, so, if you say like, okay, how do I build a free resolution? Well, the first question is like, how do you build W0? And building W0 basically amounts to just picking generators for M. Yeah, so we're going to, free resolutions always exist. This is, probably many of you, if not, have seen homological algebra. I'm not going to use any facts from homological algebra. This is all just like for analogy. When you're constructing a free resolution, there's sort of two extremes. One, you might want some small resolution to help you do calculations. You also might want some huge resolution that has nice functorial properties, but maybe is computationally not tractable. And that's the one that we're going for here, because we're not calculating anything. So my question is, let M be an R module. What's a natural generating set for M? And don't make any choices. I mean, you can't make choices because I haven't told you anything about M.
Yeah, M itself.
M itself, yeah. M generates M, so that says that R of M. So here, just view M as a set is surjective, and R of M is free. I guess like eventually we'll want maybe the reduced version of this. You don't need 0 to generate M, but it's fine to throw 0 in for right now. So and what are relations? So M is going to be W0 modulo F of W1. So you can think of S0 as generators and S1 as relations. So let's say we took this stupidly big set of generators for Z mod 7. What they're going to be relations. Relations are just things in the kernel. What's an example of a relation? Like what's in the kernel of free abelian group on Z mod 7 mapping to Z mod 7? Oh, just a quick, like, here's a fact that probably all of you have known, that but some of you may have forgotten. Abelian groups are the same thing as Z modules. So if I'm switching back and forth between modules and abelian groups, I'm just viewing abelian groups as an example of our modules. Yeah, so okay, this map is not injective because this left group is infinite. This right group is finite, so clearly there are things in the kernel. Yeah, well.
Yeah, like 7 anything, right?
What?
7 anything.
You're saying like 7 times, 2. 7 times 2 goes to 0. Yeah. Here's maybe a, that's one kind of thing in the kernel. You're using relations in Z mod 7 to get relations in up here. So we have sort of 7 lives in Z, but it doesn't, 7 is not 0 in Z, but 7 is 0 in Z mod 7. Another, here's another dumb way to get relations. 1 times 2 minus 2 times 1. Right, like this. So here, this, maybe I'll color coordinate. The blue is in Z, and the red is in Z mod 7. And if you want, you can actually think of, this, like, where's a minus sign? It's not a minus sign. You can even think of your class, your example as being a subcase of my example. But now this 7 is 0. Right? Because this 7 lives in Z mod 7. So the 7 on the right is 0. The 7 on the left is not 0. So this whole class is not 0, but the second term is 0. Okay. And in fact, classes of this form generate the kernel. Yeah. So you can take, now these things are getting incredibly large. You can take W1 to be the free R module on the free R module on M. And you can let map F1 be given by, so we have a formal sum of formal sums of things in M, and there's sort of two ways of composing. You can multiply like this, and you can multiply, you can multiply the RIs, or you can say, hey, this formal sum, I can just view as an element of M. So you get a difference of these two terms, and these two terms are exactly like the 2 times 1 minus 1 times 2. Yeah, so, the proposition is that this is exact. So, this map is going to be the alternating sum. So you think of like what's the first map? The first map is you somehow have R act on M. The second map is the difference of having R act on M and R act on each other. Yeah, any questions before I sort of go on to the next slide? Okay. Yeah, so we'll let like W minus 1 be M, and in general let Wi be free abelian group on Wi minus 1. So that's just going to be R free abelian group I plus 1 times on M. And then we'll let Fi be the alternating sum of maps induced by, well, there's like the combine the R terms maps. So we'll have, I don't know, many of those maybe. Or I minus 1 or plus 1, I don't know. And then we'll have one of the maps is going to be just like the fact that M is a module, we get a map like this. And then the claim is that this is a free resolution of M, that this is exact. Yeah. It's clear that this is surjective, and maybe is less obvious that this hits everything in the kernel. It's clear that it's in the kernel, but yeah. You can check that this is exact, and this gives you a functorial free resolution of a module. It's stupidly huge, but if somehow you're interested in formal properties, sometimes this might be better than some small resolution where you like say, oh, I'm gonna pick my favorite generating set, and then I'm gonna pick some small set of relations, etc. Yeah, so you can do the same thing with monads, but instead of being a chain complex, you're going to get a sort of a simplicial gadget. So if you let let M be a monad. So this is maybe bad choice of letters. So M corresponds to R, and A corresponds to M. Yeah, I'm sorry that like monad and manifold and module all start with M. Yeah, so you should think of like M as analogous to the ring, and A is analogous to the module. And we're going to build a resolution that's going to be, or maybe you should think of M as analogous to the free R module functor. So A is going to be an M algebra, and we're going to build this simplicial gadget. So this is going to be a simplicial space, or assuming A is a space, and M is a monad in spaces. So WP is going to be apply the monad P plus 1 times to A. And then we're going to get these maps dj from wi to wi minus 1. And what you're going to do is you're going to, most of the time, you're just going to use the monad multiplication to combine, to compose two of the M's. And for one of the maps, you're going to use the monad multiplication, or you're going to use the algebra structure map to map MA to A. So you either use the monad structure or the algebra structure to cross off one of the M's. Yeah, and so this whole gadget has the structure of a semi-simplicial space, and we're going to prove that it's equivalent to A. And level-wise, the entries are free. So we're thinking of this W star as a free resolution of A. And in fact, I'm gonna name this. I'm gonna often call this M bullet plus 1 of A, because the space of P simplices are going to be M to the P plus A. Yeah. So this WP. Okay, so in the so now I'm just going to sketch a proof of the recognition principle, and then I'm out of slides, even though I won't be out of time. Yeah, so what's the idea? So A is somehow equivalent to, this is like the free resolution of A. And then what we're going to do is we're going to use the fact, I'm missing a bunch of n's. There should be n's here. That Cn blank is going to be equivalent to loops n suspension n blank by the our scanning result. So that's going to say I can replace the outer cubes n by this loops n suspension n. And then what we're going to do is then we're going to pull out this loops n. So we're going to get that A is the loop space of this geometric realization of a simplicial space. And the proof idea is, this is analogous to it's going to be analogous to the theorem about abelian groups. Any property that's true for free abelian groups and preserved by taking homology is true for all abelian groups. But here, like chain complexes don't really make sense in the category of spaces, but simplicial things do. So instead of our resolutions being simplicial, or instead of our resolutions being chain complexes, there'll be simplicial gadgets. Yeah, so the next at least 2, maybe 3 lectures, I can't count. There are 3 classes before Thanksgiving. Is that correct? Yeah. The next lecture.
There's also the Tuesday before, right?
What?
So aren't there 4? Isn't there also the Tuesday before Thanksgiving?
Oh yeah.
So it's 4 classes.
So maybe we have 3. It'll take us 3 lectures to fill in the details of this proof sketch. But morally, it's just you prove it for free things. and then you construct free resolutions. Yeah, so that's where we're going, and then we'll prove bot periodicity. Okay. I'm going to stop the recording, but people can ask questions.